Okay, hello everybody, good afternoon. Welcome to this session, parallel session 7, which is about offshore energy system integration. My name is Ross McKenna from the University of Aberdeen, and I'm your chair for this session. I'm joined by two colleagues who will also be presenting. We have Luca Riboldi from NTNU and Rafael Martinez from University of Birmingham. This session is about, the name suggests, offshore energy system integration with a focus on two main sectors. So that's the oil and gas sector and the renewable sector. So we're looking at challenges of integrating these two sectors based on different energy vectors, storage, and transporting this energy in some cases to the shore. So I suggest we make a start. I believe Luca is the first presenter. So Luca, I'm going to share, before we start, so the format is we're having 3 presentations, and then at the end we will have a combined discussion. So please save your questions. By all means, enter them in the chat. We will be discussing those right at the end. Okay, Luca, so over to you.
Thank you, and good afternoon, everyone. I'll now try to share my screen or my presentation. So please, Russell, let me know if it's visible for everyone.
Looks good, yes.
Perfect. So welcome. My name is Luca Riboldi. I am an Atlanta Associate Professor at the Norwegian University of Science and Technology, NTNU. I'm also a research scientist from Syntex Energy Research, but today I'm presenting with my NTNU University hat, and I will be presenting about hybrid energy systems to decarbonize the offshore oil and gas sector.
Right, Luca, could you make it full screen? I'm currently seeing your, maybe you have it on the other monitor or?
Sure, there should be swap. Does it work now?
Yes, perfect, thank you.
Thank you. Okay, I will start by giving the background and motivation to this work. So it's clear that we are here because to meet the climate targets in Europe, we need far-reaching changes and rapid energy transitions across all the industrial sectors. Among those, there is also the oil and gas sector that, although is directly responsible for a small share of the entire amount of greenhouse gas emissions, its contribution is relatively larger in certain countries. For instance, Norway, where actually it is responsible for up to the 27% of the national GHG emissions in 2020. So it becomes clear that if Norway or similar countries needs to decarbonize and meet their national pledges to reduce emission, also the oil and gas sector emission needs to be addressed. And indeed, the Norwegian oil and gas industry has announced some relatively ambitious goals with an objective of reducing emission by 2030 of 40% and a further decline to near zero in 2050. So how to achieve that? There are different possibilities. A first group of known and mature technologies use entails the improvement of energy efficiency, so mainly energy efficiency measures. An example are the utilization of combined cycle. However, a survey of the literature shows that this would bring down the emission of a maximum of 20–30%. So it's good, a good first step, but it's not sufficient. Second group of technology, which starts to become a bit more interesting, is the integration of renewable energy, normally in the form of offshore wind, but there are also other possibilities like wave, tidal energy, or even floating photovoltaics. but normally we are talking about the wind, and then this could lead to a potential CO2 cut of 25 to up 50% if one surveys the literature in the sense. Of course, there is a big range because it depends on the capacity of the renewable energy which is integrated in the system. But we want to approach up to 100% emission reduction. So what can be done in this group? Actually, we have quite a heterogeneous type of alternatives. So, for example, we might be thinking to implement CCS, carbon capture and storage, where CO2 is captured on site and stored in underground formation, like depleted reservoirs. Alternatives are electrification, so basically getting power from shore by laying subsea cables. So that is a possibility, and of course would lead to a quite extensive local reduction of CO2 emissions, which would go close to zero. But there are there is still some debate about the overall effect. And indeed, in 2019, we had an analysis looking on the effect on the European power system of electrifying a large offshore area in Norway. And the results is that the potential for decarbonization is really dependent on the methodology that is selected to associate a carbon footprint to the electricity sent offshore. The third type of technology and the focus of the presentation today is the utilization of hybrid energy systems, which in a way would leverage on the possibility of integrating renewable energy, in this case in the form of offshore wind, but would try to maximize its impact by also adding the possibility of energy storage. And in this work, we use hydrogen as the technology for this. So starting from this premise, the objective of our work has been to verify what could be the potential of a hybrid energy system to decarbonize offshore. So we developed a concept that we call the HESOF, which stands for Hybrid Energy System for Stable Power and Heat Supply in Offshore Oil and Gas Installations. So in here, there is a simple scheme of this concept. And if I succeed to have a pointer, I'll try to guide you through this. So if we have an offshore installation, which needs heat and power for running its processes, we have first source of power, which is a wind farm, which is developed nearby, which sends power. But we know that wind is an intermittent source of energy, so we would need to complement this with something else. The first option is to utilize gas turbines, which would provide some baseload power, and importantly also would provide heat, which is needed as power for the operation of the offshore plant. Heat which is harvested from the waste, from the exhaust gas of the gas turbine. But another possibility in here is when we have a surplus of power from the wind farm, we can send this excess power to an electrolyzer stack. In this case, we are considering a PEM electrolyzer technology, which convert this power into hydrogen. Hydrogen that can be either fed to the gas turbine to decrease the carbon footprint of its power production, or be stored and later be used in a fuel cell stack, again a PEM technology, as backup power, to be used as backup power whenever wind is not blowing. So this is the concept that we were aiming to assess. And this concept has been presented and is available in the literature. In order to run this assessment, we developed an integrated model. On the one end, we have what we call the process model, which are the sub-models of all the key process components, from a model of the gas turbine, of the energy storage, intending with these the fuel cell and the electrolyzer stacks, model of the wind turbines, and so forth. But since the objective was not just to provide heat and power, but also to provide stable power, we also developed a model of the electrical grid, offshore electrical grid that has been modeled with a surrogate model. And these two were put into communication in order to exchange information, and that eventually allowed to run two types of analysis. One that we called long-term analysis, which is mainly based on the process model, and there's a time resolution of hours, which allow to evaluate what could be an ideal or at least effective process design, to evaluate what could be some feasible storage strategy, and to assess the amount of emissions or how much we are able to curb emission with this concept. The second type of analysis is called short-term analysis, and there's a different time resolution. We are in the domain of seconds, and there's as main objective to evaluate the grid design, or in other words, to evaluate if we can ensure with the process design developed frequency stability and comply with other industrial standards. So the integrated model allowed us to develop a design routine, which then eventually has been inserted in an optimization algorithm. The routine starts by defining a process design in terms of type of gas turbine, size of the wind farm, capacity of the fuel cell and electrolyzer stacks, and so forth. And first run the so-called long-term analysis that returns us first the ability to supply it during the entire lifetime of the plant the required heat and power, but also the CO2 emission obtained and the size of the hydrogen storage, for example. Once this is concluded, the information are passed to the electric grid design, which then starts the short-term type of analysis and check whether the process design identified is able to comply with frequency requirements. So if the maximum frequency deviation is within the limits, and also, for example, if the gas turbine ramp rate, the maximum one that we obtain, is within the manufacturer limits. If grid constraints are satisfied, this design is stored. Otherwise, some feedback information are provided to improve the process design. As I mentioned before, this has been also included in an optimization algorithm, and we could run some optimization simulations, and where our main objective was to decrease the cumulative CO2 emission, that is the emission throughout the entire lifetime of the operation of the offshore installation or area. This optimization has been as well developed last year and is available in the literature to be checked. So some of the results that we obtained. So this that is shown here are some Pareto fronts of optimal heads-off designs. We obtained several of these Pareto fronts with different characteristics and with different information provided. The one that I'm showing now is in blue, the Pareto fronts that the optimal design that we've been obtained without taking into consideration grid limitations. In orange, when also grid limitation are included. So what we could see is that it's interesting to see that the designs that were leading to the lowest possible emission, but also the largest hydrogen storage size, were actually discarded when we were taking into consideration grid limitation, because they were not able to comply with this, to ensure grid stability, let's say. So this, in a way, is we saw it as an indication of the importance to include this grid stability type of consideration already in the design phase, to being able to find those designs that actually are feasible also on that ground. But as I was saying, the most important parameter that we were checking were the cumulative CO2 emission. We want to decrease emission. And if you're looking in orange, the cumulative emission of a simple cycle gas turbine cycle that is used offshore, which is the standard way of producing energy for in offshore areas, we can see that the SOF concept was able to reduce emission by approximately 40%. We made also an additional comparison against the most basic way of integrating renewable power, which is having a wind farm and then making that working in parallel with some simple cycle gas turbines. And we see that the SOF concept is actually able to reduce even in comparison to that emission, but only of about 40%. So both in absolute terms and in relative terms, the emission reduction were not as big as expected, although we should also mention that we noticed that the SOF concept was able in general to increase grid stability and allowing for integrating larger and larger sizes of wind farm, which would be more constrained with normal integration. But we wanted also to investigate why we were not able to achieve carbon emission more than that. So we started to look at what's happening if we are integrating an increasingly larger wind farm. It's here in the x-axis. And what we notice is that our SOF concept seems to plateau in its ability to decrease emission, even when the wind farm size is increasing. So initially we thought this could be due to design limitation, for example, in the size of the electrolyzer stack or fuel cell stack or at hydrogen storage. So we ran another type of simulation, which we call SOF ideal, which is with unlimited capacity of the energy storage system. But we still saw that we got just a relative improvement and the emission were still plateauing. So we started wondering whether this is really the limit of the SOF concept. In order to figure that out, we started to make some additional analysis, and we noticed that the preliminary indication pointed to the fact that a key to exploit the full decarbonization potential would actually be to figure out the best way to supply also heat to these offshore installations, not just focusing on power, in other terms. In order to evaluate if that's really the way to go, we modified the SOF concept to allow including different sources of different technology to cover the heat demand. So we have a theoretical case in which the heat demand is met by internal heat recovery, so exploiting the waste heat available from the processes offshore, which of course the feasibility of this would be case specific. Then we have the utilization of waste heat recovery unit from the exhaust of the gas turbine. That is the standard SOF concept that I presented before. But in addition, we also checked a power to heat configuration via the utilization of electric heaters and a gas-fired heater possibility in which we are sending a mixture of methane and hydrogen to the gas-fired heater in order to meet the heat demand. We ran simulation for all these cases, and in this figure, I will show the results that we obtained. So the gray area is the emission that so above the emission that we would obtain with a standard gas turbine simple cycle. So we don't want to be in this area. And again, we have been testing these for different size of the wind farm integrated to the system. What we saw is that integrating waste heat recovery unity as before led to a quite significant initial decrease of emission, but then plateauing to again around 40% relative CO2 emission reduction. But when we changed the technology to supply it, for example, using either an electric or a gas-fired heater, we noticed that we obtain a more direct correlation between the size of the wind power that is integrated to the system, and the potential to reduce emission, which for a 50 megawatt wind farm could reach over 70% relative emission reduction. Finally, we tested the theoretical internal heat recovery case, and as expected, that is the best one that one could obtain, because basically you're exploiting the heat that is already available in these offshore plants, and we were able to reach up to 80% emission decrease. This analysis has been recently summarized in a paper which is being submitted, and so hopefully will be published soon as well. One last slide on my side with some closing remarks on the work that we've been doing on assessing a hybrid energy system to decarbonize offshore. We noticed that very large CO2 emission reductions are possible, up to 80%. But that entails the proper selection of hybrid energy system design, which needs to be able to supply in an efficient way both heat and power. And the best design might be to some extent also case specific. Something that should be mentioned is that so far we've been checking what is the environmental performance of this, but we haven't yet assessed the economic viability, which we believe there would be an important aspect to check to see if these systems are really a possibility for future offshore installations. Finally, I would like to spend some words on a comparison with other potential concept to decarbonize offshore. The first one is a comparison between the hybrid energy systems and the integration, the simple integration of renewable energy sources with gas turbines, for example. So hybrid energy systems, in this case, has the advantage that that can lead to a larger potential for CO2 emission cuts. And we also notice in our analysis that they might increase the grid stability. The disadvantage is expected to be in the increased capital investment. But as I mentioned before, that hasn't been assessed yet. Finally, some words in terms of a comparison with offshore electrification. So the utilization of hybrid energy systems entails that there is no competition with other sectors for power. That could be an important factor, especially in the shorter term, where there is maybe not so much availability of clean electricity. Another advantage is that the hybrid energy system can be developed in cases where electrification is challenging, like remote locations or long distance from shore. And at last, an important aspect is that the hybrid energy system offshore has a larger potential for reuse of the infrastructures. In fact, when the oil and gas reservoirs are depleted, they could possibly become some sort of energy hub where, for example, hydrogen is produced and either exported onshore or maybe used for other offshore sector like maritime transportation. And this I conclude. I thank you for your attention, and I will be happy to answer questions at the end of this session.
Great, thank you, Luca, for exciting, interesting presentation. I don't see any questions or hands urgently in the chat or whatever, so I guess we will just move straight over to my presentation, and also in the context of that it wasn't intentional, actually, the order of the presentation, but it is a nice order. I've just realized because we have Luca looking at the individual sort of platform scale. And I'm going to present to you now about a study which is looking at the Danish sector, offshore sector, and then Raphael is going to talk about the whole North Sea region. So hopefully, could somebody, maybe Luca, just confirm that you can see this?
Yes, it's on the screen.
Oh, perfect. Thank you. So as I said, yes, this study is about the Danish North Sea. and it is a collaborative project between University of Aberdeen and the DTU. And the context for this study is essentially we wanted to analyze for the Danish offshore region, or otherwise known as the Danish Underground Consortium. So essentially a set of offshore infrastructure and assets which are owned and operated indirectly by Total. We wanted to analyze for this offshore context what synergies there might be in the future years and decades between existing oil and gas infrastructure and developments in renewables, in particular offshore wind infrastructure. So you can see on this map the context of the system that we're looking at. Here we have existing offshore wind parks. A little scale here for maybe I can do the same. Yeah, so we've got some offshore wind parks here. We have existing pipelines, gas pipelines, and oil pipelines. Then you can see that most of the oil and gas fields are of the order of 200 kilometers, at least 200 kilometers from the shore, in some cases more. What you can also see is the bathymetry, sort of the sea depth, and you can see that it gets quite a bit deeper as you go further out. So these existing offshore wind parks are fixed bottom foundations, but as you get further out, the depth of the sea is quite limiting for those, which is why in the study we were particularly interested in floating wind parks. So we've got the oil and gas clusters. Each of these is a field consisting of several platforms which are interconnected. And these platforms and this whole infrastructure is facing several challenges, obviously, across the oil and gas sector. We have, as well as uncertainty around prices for oil and gas. We have emissions reduction that must be achieved during the lifetime. And then we have, I feel like, the ultimate challenge for this sector, which is that of decommissioning, which is the legal requirement that this infrastructure has to be removed. And obviously, there's a significant cost implication of this decommissioning. So, some of the ideas we were exploring in this project were to what extent can exploiting synergies with perhaps offshore wind, but also hydrogen production, how can that help to alleviate or sort of reduce some of these emissions? So in terms of the technologies considered, we looked at essentially electrification during the lifetime. Luca also talked about, and we looked at then repurposing, partial decommissioning, and repurposing. So the idea with electrification is that we can install one or more offshore floating wind farms and essentially replace the existing gas turbines, which tend to be the main source of power on these platforms. And that is feasible, obviously, in the short term, and it makes sense to do that during the lifetime of the platform. When it comes to the end of the life of the platform, in anything from the next decade to out to 2050, we additionally looked at the possibility to repurpose or partially repurpose this infrastructure. Essentially, we assume we can replace this top side, which is everything, pretty much everything above the water line. We can install a new top side, which is then used as a hydrogen production facility with electrolyzers, which are powered from the floating wind farms. This hydrogen is then assumed to be transported to the shore using either existing pipelines we had in one scenario. In an alternative scenario, we also looked at the cost of building a completely new pipeline to transport the hydrogen. You can see on the figure that CO2 is looked at. That was one of the options we originally intended to look at. We did do in the report, looked at the very high level feasibility of storing CO2 in the Danish fields, but I'm not going to go into that in this presentation. So in order to model this whole sector, this whole offshore region, we used the Balmoral model from DTU, which is a whole system cost minimization. And the decision relevant cost components that we considered there were, on the one hand, the investment or decommissioning of new or existing plants, so energy plants, but also the oil and gas platforms. And we implemented this decommissioning cost essentially as a negative cost that could be saved if the plant is not decommissioned when it reaches the end of its life. And on the other hand, we also have operation and variable cost for fuels of various plants. And you can see the assumptions here on the right-hand side that we made for natural gas, and here bottom right for CO2 taxing in 3 different scenarios. So we use the planned developments of offshore wind as far as possible, or as far as these are known, based on 10-year developments plans and offshore wind projections. We look at the horizon to 2050 with 6 modeling years from 2025. An important point, as with many of these energy system models, is that we take the perspective of the system planner. So we don't consider individual operators. We do look at the whole system optimization, something I'd like to come back to in the discussion. Natural gas prices probably a little bit out of date now, considering the current levels that we're seeing. But that was then the market price and the development from the Danish. Same applies to CO2. But one thing I'd just like to highlight here is the way in which we actually modeled hydrogen or didn't model hydrogen, as was the case. So due to constraints in the project, in particular the relatively small length of time and resources that we had available, we chose a workaround to account for hydrogen. And essentially, it's not modeled as a commodity. Instead, it is accounted for indirectly through a large increase in electricity demand, which is assumed to be used in the transport sector. This is based on a lot of published studies that estimate this increase to be likely to decarbonize the transport sector, and allows us to allocate this hydrogen demand accordingly. The model can allocate this demand between all countries, including the model that you can see here in the figure. So it can decide how much hydrogen it wants to produce in each region based on a cost minimization and based on the quality of resources. For example, it could decide in France to install lots of ground-mounted solar, then generate electricity. Having said that, the maximum demand allocation for hydrogen in each region is capped, so it couldn't generate all of the hydrogen in one region. And the overall demand for hydrogen then increases till 2015 because of the anticipated development in the transport sector across these countries. So it's important to note or to emphasize in that context that the allocation of the hydrogen production, when we look at the results, is seen as optimum in this larger context, right? So we're not just looking at the Danish oil and gas sector, we're looking at this sector in the context of all these neighboring countries around the North Sea region. Okay, so I mentioned repurposing, and there have been quite a lot of studies in recent decades about repurposing and the associated costs. So for our assumptions, we looked at the sources you can see here, bottom left. A lot of those coming out of a lot of those coming from the UK context, in particular the Oil and Gas Authority. So what we assume is that the wells, the jackets, the pipelines, and the subsea structure can be used as they are, as I said. So we save the decommissioning costs of these structures. We then further assume that 50% of the platforms can be renovated. The reason for this 50% is that not all are feasible for this repurposing, perhaps due to their size, due to their configuration. Some of these satellite platforms are a lot smaller than the main ones in these fields. We assume new topside is installed. We assume that the cost is 30% of the full decommissioning. This was based on initial discussions with the DHRTC, so the Danish Hydrocarbon Technology Research Centre that funded the research, and also based on literature estimates. So we assume the topside has the same weight as the old one, and so essentially it becomes a cost of 40 euros per kilogram. So in terms of this breakdown in the pie chart, what we're essentially saying is we save, we don't need the well abandonment cost, or essentially we save all of the subsea fractions, right? So well, abandonment of the subsea, the removals and the owners costs lead to the fraction of that. Coming on to the scenarios, so we looked at two main scenarios. As you can see here, the first one is what we call business as usual. This is assuming that all gas platforms are decommissioned according to the timeline, which is based also on expert discussions and estimates around the anticipated climate schedule for these piles and these reservoirs. Second main scenario is what we call electrification and repurposing. This is where the model has the option to electrify the platforms during the lifetime and then repurpose them. Sensitivity analysis then involved further 7 scenarios where we essentially vary parameter inputs such as the floating wind cost, the transmission line cost to shore, the CO2 price or tax, as I showed previously, and the aspect of pipeline use. So whether we can use existing pipelines or whether we need a this is a big question in the research about repurposing, especially because of the issue of hydrogen embrittlement of steel. So moving on to the results, what we saw in the bow scenario, remember this is business as usual, so this is assuming that there's no decommissioning operating as usual, but electrification is possible. No, sorry, not sorry. In this scenario, nothing is possible. So this is just to show the reference case. So what you can see is for the different platforms, what I should have said at the start is that we aggregate the platforms to fields, and these are the 5 fields we considered. And the CO2 and fuel-related expenses increase towards the end of the life of the respective field because of the assumed increases in CO2. No massive surprises there. One thing we didn't consider that's important to note is the operating costs. Right, so the non-fuel operating costs were not considered. But here you can have an idea of the costs of each of these fields as they develop into the future and where the costs suddenly stop. This is the year of abandoning or decommissioning this. Looking then at the second scenario, which is where the electrification is possible. Here in this one figure, we have combined on the left-hand side the costs in million euros, and on the right-hand side we've got on the one hand CO2 emissions, and the second axis there we've got share of Denmark's total CO2 emissions. I don't want to go into all of the details for each of the clusters or the fields here, but the main message here is that through electrification and also through connecting these platforms to floating offshore wind, we could achieve pretty large cost savings of the order of 130 million euros. CO2 emissions about the same, million megatons. You can see what impact that has in terms of the CO2 emissions applications for the sector. When we talk about repurposing, what we need there is converting the existing platform to a hydrogen, essentially a hub hydrogen generation hub, which is powered by a floating wind. You can see the breakdown of the cost for doing that. So it's the hydrogen electrolyzers, mainly the plant capex and opex that account for the large chunks. Here, 40% and 20% overall. Then you've got floating wind and various smaller fractions for decommissioning, for reconstruction. It's by far the hydrogen infrastructure and the actual wind farm that is the largest chunk of the overall cost. Then we move on to the second scenario, the development of the floating wind. So what we see here is the development in 4 different scenarios. Remember, we have these parameter variations and CO2 price. This is the electrification reflexive scenario and the basic assumptions. Then we have floating wind, low cost, and then we have the transmission line. And what we can see is that in the reference scenario, floating wind is installed from 2045. Here, and then the 2 fields, Hartdown and Tyra. So these colors here, this one here, have the largest share of floating wind. At the earliest, floating wind is installed in 2035. And that's with a particularly low cost or an ambitious cost development for this technology. And it reaches aggregated capacity by 2050 of almost 6 gigawatts. And this is across all of the analyzed platforms. Looking at the hydrogen production capacity, this relates or correlates to the floating wind capacity, as you might expect, because it's the floating wind that provides the power for the electrolyzer. So we see a similar picture there. Hydrogen is produced from 2045, so essentially this panel bigger. In the same fields, Hartdown and Tyra, but also Harald are the first ones to produce. What we see is about 3 gigawatts of electrolyzer capacity for hydrogen spread across these fields. And if the floating wind cost is reduced, once again, we already see hydrogen production in 2035. But nevertheless, this is still some years, or even in some cases decades, from the date of anticipated end of life of production of some of these platforms. So I'll come back to that also in this slide. So what does the system look like in 2050? Well, this figure, remember I showed you at the start the overview of the sector as it looks today. Well, this map gives an overview of the system as it may look in 2050 based on our analysis. So this here is the planned Danish island with 10 floating parks attached to it, or some future wind farms associated with it. These are planned wind farms connected to the shore, and here we have the floating wind farms that are connected to the various oil and gas fields. We also have color-coded interconnectors, which are on the one hand for electricity. So we see that most of these fields are connected to the island and to shore in order to integrate them with those energy systems and enable the transport of power in both directions here. And the pipelines, as I showed before, already exist. Apart from the new pipelines that in some scenarios we actually choose to build. can see the temporal development as well. So essentially some of these connectors, these, for example, to the island and to the shore are already built in 2035. Remember, that's the first model year. Right? So as soon as the platforms are electrified, it makes sense to connect these and to integrate these with the rest of the entities. Whereas the pipelines for hydrogen are only used in 2050. Okay, moving on to the discussion. So I just wanted to highlight, obviously the hydrogen modeling was indirect because of the way we considered an increasing demand for electricity in the transport sector. So that could definitely be improved and should be improved in future studies. Spatial resolution was a little bit rough or very rough, you might say, especially the way we aggregated quite large oil and gas fields into one node, essentially. And this includes, as mentioned, several platforms, which should undoubtedly be improved. There are some issues around technical feasibility. So Luca talked to us about heat demand. That's one thing we didn't look at all in the study. So, during electrification, some of these platforms need heat. They currently get the heat from the gas turbine, from the heat that they recover there. So there's an issue here around feasibility of providing this heat with the floating room. There's also an issue around replacing the top side because some of this infrastructure is up to 50 years old. So the structural integrity is not necessarily given, or not necessarily lasting over 30, 40, 50 years as we plan in the study. There are quite a lot of uncertainties around the cost and the operational costs, not just for fuel, but also CO2 and operational costs we didn't consider. Another quite big issue is around the timeline and the temporal resolution. So I mentioned some of these platforms are already decommissioned in 2025 or 2030. In some cases, these are not used again or not repurposed until 2040. So a decade later, actually. So there's obviously an issue there around how well the storyline's timeline actually makes technical economic sense. Final issue is the perspective. So we have the system perspective with minimization of total costs. We don't reflect any subsidies there or incentives for hydrogen or green hydrogen, for example, in the future. We also don't reflect individual perspectives of operators and whether this economic analysis that we did in the study makes sense for individual operators. Just to sum up now then, we did an energy system analysis of the synergies between oil and gas and renewables in the Danish North Sea. We found North 2050. Main results were that through electrification, which is essentially immediate, we can save 70% and 85% of cost and CO2 respectively. The energy system integration aspect involves an immediate connection of platforms to offshore islands and to the shore. And saw substantial hydrogen production capacity with 3.6 or up to 3.6 gigawatts and just short of 6 gigawatts of floating wind, which is a potential to avoid decommissioning costs. What I should have mentioned is it potentially offsets these costs. Of course, it doesn't completely avoid them because at some time in the future this infrastructure may. What I didn't mention in the slides was that we had an LCOE of hydrogen of about €4 per kilogram, which is higher than some existing studies. And we didn't consider support policies and incentives for green hydrogen in the future. And we did have several limitations. That's the end of the presentation. I'd like to thank you for your attention and just ask for any immediate questions. If there are no immediate questions, I would pass on.
We have a question from Tom, I think.
Yeah, I had a question. Thanks. Nice talk. You have these 3 gigawatts of electrolyzers on the platform. Is that the idea? I mean, that seems quite a lot. I mean, you mentioned the operational costs being a bit uncertain. I mean, what would it cost? What would the maintenance requirements be, for example?
Yes, the idea was to have maybe you joined late, it wasn't clear, but we're trying to have questions and answers at the end of all the presentations. So unless there's a question that's specifically about understanding,
Okay.
to clarify.
No, it was more a general question.
More general question. If I could ask you to come back with that question at the end, then hopefully all three of us will have a chance to respond and discuss. Yeah, that's great. Thank you. Just trying to get back to.
Okay, so should I share my screen then?
Yeah, I'll pass it over to Raphael now then.
I think you need to give me permission to share the screen. Because I'm only a participant here. I have the message host disable participant screen sharing. So apparently I'm not
Work
able.
now?
Yeah, now I can. Yes. Can you see the screen?
Yes. Looks good.
Okay,
Go ahead.
perfect. Okay, thank you. Well, first of all, I apologize for my voice. I have a bit of cold, so I will try to speak loud. But if at some point you cannot listen, just please let me know. I will try to speak a bit louder. Well, I'm Rafael Martinez. I'm currently a PhD candidate in the University of Groningen, and I will present today some findings we got from a recent study, which basically is called Modeling the North Sea Energy System Benefits of an Integrated Power and Hydrogen Offshore Grid. So first, a brief outline. I will first present a model, the SINS model. This is a model we developed together with TNO during the last almost 3 years. So yeah, the first part of the presentation will be a bit more methodological. And then I will move to 3 specific case studies, which are more related to the system integration topic, which is what brought us here, which is a case for the whole North Sea energy system in 2050. Another case of an offshore power grid, and the last one in which we also included a hydrogen network as well. So a combined hydrogen and power offshore grid. But yeah, first I will start with the modeling part, which is the more methodological one. And the first question that comes is why we need another energy model, because as most of you probably know, there are many energy models out there, many open source models, many good ones. So why we need to bring another one? And well, the reason is that the North Sea is a very particular area. So we found that there are many aspects that deserve extra attention. As you all know, the North Sea is a very busy maritime area. You can see on the right side. A simple example of different energy, uses of the North Sea space for fisheries, shipping, oil and gas extraction, sand extraction, military use, natural 1,000 areas. It's quite hectic. Of course, there's a large oil and gas infrastructure, as we saw in previous presentations, that could be repurposed for energy use. It's highly populated. We have around 200 million people living around, which of course drives the energy demand up. We also have a lot of industry clusters that are very energy intensive. It's highly interconnected in terms of energy as well. And as we know, offshore wind is expected to play a major role. So yeah, all these characteristics deserve special attention in an energy system model. The fact that there are multiple spatial claims invites us to think that the high spatial resolution should be preferred in an energy model that tackles the North Sea region. We expect a large deployment of intermittency. So to be able to use hourly resolution, it's also a asset in a model. And yeah, the high interaction between energy sectors should be covered with a high sectorial coverage to try to capture this sector coupling. And yeah, if we add more things to the wish list, there's high interaction between countries. So the larger the geographical coverage, the better. So if we try to combine all these wishes, all these features, then it gets more difficult to find a model in the literature that can bring this to the table. So that's why we developed what we call the ESINS model, which stands for Integrated Energy System Analysis for the North Sea region. which is a model developed within the ESA-OPT framework, which has been developed in the last 2-3 years. And initially was a model only for the Netherlands. It is already published and it's well established in the literature. And yeah, recently we enhanced it to cover the whole North Sea region. So I will briefly give some details about the modeling framework, but in case any person wants more details or is interested in how the model works, I can also provide some more documentation and some other publications. But yeah, just in a nutshell, just as a summary, the ESINS model is a cost optimization integrated energy system model that minimizes the typical objective function of these large-scale models, including investment, retrofitting, fixed and variable costs. It's written as an LP to keep a relatively simple and manageable computational need, because the problem size is very big. So we need to write it as an LP to have relatively short solving times. It includes the complete sectoral coverage of 7 North Sea region countries, that is the Netherlands, Germany, Denmark, Sweden, Norway, UK, and Belgium. So all the energy sectors of these countries are included. The offshore part, so the North Sea, can be described in a tailor-made way. So the user can define how many nodes to include offshore and how many activities to include. So that's perfect to analyze system integration, case studies, or electrification of platforms, because we can put as much detail as we want. And yeah, it's the code and data and all the knowledge we're developing is open source. The model now is written in AIMS, so unfortunately software is not open source, but yeah, as I said, code and data and the publications we're producing, everything is under open source principles. So just a brief description on how the model represents every country. Every North Sea region country is represented, as you can see here in this box. So we basically have all the sectors, all the energy sectors, either residential, service, agriculture, industry, and transport. And we have different drivers, for example, iron production, chemical production. We can describe in a very detailed way what are the future drivers of the energy system. And we have different energy activities, electricity, heat, natural gas, hydrogen, refineries, and biomass, and different levels within these activities. We have high voltage, medium voltage, we have high temperature heat, low temperature heat. And yeah, of course, all these activities have related CO2 emissions. We also consider them either ETS, non-ETS, and CCUS network. Also international emissions, so we can consider all the greenhouse gas emissions of the system. And yeah, we have all the primary energy commodities, like coal, natural gas, uranium waste, etc. And just to close a bit how the model works, that's a bit the model structure. It's, I think, quite simple and quite similar to other models. Input data required is mostly macroeconomic data to see future volumes of industry, transport, etc. We need technology data in terms of learning curves, how much the technologies will cost in the future, a bit of policy landscape to see what are the mitigation targets and evolution of primary energy in the future. Yeah, and the system basically minimizes the detecting function following a set of constraints, which are hourly for the power sector and daily for the gas sector. And all the results are provided in a very sophisticated user interface that was developed by a colleague in Tieno. I have, I think, here a short description. So basically you can browse and you can explore any result that the model provides in a very simple way. And you can find every year of the simulations for every technology. You can see any profile or any output that the model provides in a very interactive way. And yeah, I think I mentioned this before, but the system representation of the 7 North Sea region countries is complete, but we also include in the model the power network of the whole Europe in order to capture import and export dynamics with surrounding countries. We also have a gas network with neighboring countries. Yeah, and as I said, the offshore nodes can be tailor-made. So that's all related to the system, to the model specifications and how the model works. As I said, if any person needs more information or wants more clarifications, we can discuss later, or I can provide more information. But now let's move to case studies more focused on the North Sea, which is the main topic. The first one is a bit more general. It's about the whole North Sea energy system in 2050. This is about to be published, I hope this month or next month. It's under review now. But basically, we wanted to analyze and how the energy system of the North Sea region will look like in 2050 if we really want to go for net zero emissions. Because the trend in the last 25, 30 years is clearly not enough to meet this target in 2050, and therefore the space needs to be increased. Just as a summary, we evaluated 7 different net zero emission scenarios, modifying different parameters such as biomass availability, renewable potentials, onshore and CCS social acceptance, and different ambition strategies. For example, if we include international emissions in the national budgets or not. I won't go into detail into the results of these runs, it's kind of general and we don't have enough time, I believe. But basically, that's the primary energy of these scenarios. And key thing here is that wind is very relevant in most of the scenarios. And of course, offshore wind plays a big role there. So I will focus a bit more on that so we can zoom into the North Sea and to implications of this integration. Those are for the 7 scenarios that we evaluated for the 7 countries that we are analyzing. The offshore wind investments and the cells that are in yellow and in bold numbers are the ones that are reaching the technical limit. So interesting conclusion here is that the Netherlands and Germany are reaching in all the scenarios the technical limit that we feed to the model, while the rest of countries like the United Kingdom never reaches technical potential. That means that there's offshore wind that is not being invested because it's not cost optimal, because the model doesn't find a cost-effective way to integrate it in the system. Yeah, this opened the door for us to ask, what can we do to try to integrate this grid? And that brings us to the offshore grid concept that we were trying to evaluate. So the first dummy analysis that we did was to say, okay, UK is not fully investing in all the offshore wind resource. So what will happen if we allow these 2 simple HVDC interconnectors from UK offshore wind to Netherlands and Germany offshore wind? And what we found, and of course that's a very dummy and very simple approximation to reality, but we found that in the base case, UK was only investing in 3 gigawatts of far from shore wind. These nodes represent wind that is farther than 100 kilometers from shore, so wind that has to be connected via HVDC. And Netherlands and Germany were investing in the whole potential of Mosquito by the scenario. But the moment that we allow these additional interconnectors, yeah, UK investing 110 additional gigawatts. So the hypothesis was, okay, if we allow these additional interconnectors and we allow more connectivity between offshore wind, we can really integrate larger amounts of wind. Of course, that's a very simple approximation because we are clustering all the offshore wind of UK here in this point. That's not realistic at all. We are using 1 node per region, but this was the starting point. So we wanted to move a bit forward and get a more realistic representation of the North Sea region. So of course, using political region is not a realistic approach. We can see here offshore activities, energy-related activities in the North Sea, and we see there are many, many data points, multiple claims for space of different activities. So of course, if we define regions, it should be based on data and not based on regions defined politically or very grouped clusters. So I will pass quickly but this slide, but we basically analyzed different clustering alternatives to try to get offshore regions that were meaningful. And in the end, we went for K-means. It's pretty simple. I think everybody knows how K-means works. And we basically decided that we only want clusters based on distance. So we want to group the data based on how far away are the offshore wind deployments to each other. I think we can easily see this here in this slide. So our input data was the plan and explore areas for offshore wind development in the future. So we wanted to feed the algorithm with locations where we are certain that in the near future there could be offshore wind. And of course, we want to exclude in this methodology areas that are not suitable for energy purposes, either because they are protected or because they are used for shipping or other activities. And next question is, okay, how many nodes do we need to define? Because with K-means, the number of nodes is defined by the user. K-means gives the optimal node configuration once we know the number of nodes. And we found out different heuristics to try to find how many nodes are optimal to properly represent the North Sea region. The first one is the elbow method, which is very simple, but also very effective. It basically means plotting for a different number of clusters, what is the sum of a squared error. So basically the average error or average square distance from the different data points to the centers of the clusters. And basically we can see that if we move from 4 to 6 clusters, if we increase this number, we don't get a lot of reduction of error. So basically with the data that we have, going farther away than 6 clusters is really not very meaningful. So with 6 should be enough to represent, at least with the data that we have. And other heuristic that we used was the 100-kilometer distance. As we know, 100 kilometers is a good proxy to define where HVDC is cost effective compared to HVAC. And of course, when we cluster these offshore wind deployment areas, we want to have them as close as possible. We use HVAC cables to connect to the centers of the hubs, to then use HVDC to connect these points to shore. So again, we see the same trend with 4 to 6. We have a pretty decent representation of reality. So that's why we decided to go for 6 clusters for the whole North Sea region, which are the ones that you can see here. That's the optimal configuration that we found out. And with this configuration, we move to the model to see what kind of design we have at the moment only for power. Of course, ESINS is an LP model, so small investments in interconnectors might happen, which is probably not realistic. And we need to exogenously define what interconnectors are available, so which interconnectors the model can invest. And we decided to go for this layout, so the model can decide to invest in any of the offshore interconnectors. As you can see there, all of these are, of course, HVDC. So first, this is the result that we got using this offshore layout. And it's interesting to see only 2 interconnectors were not invested, the one between northern UK to Norway and the one between Netherlands and Germany. But the rest of interconnectors, the model decides to take them. And there's a large investment in wind in most of the offshore nodes. In total, we have 247 gigawatts. And this is only the wind that is farther away than 100 kilometers. We also have some wind that is closer to shore. Yeah, and it's interesting that areas like UK or Denmark, that when we don't have this offshore design, don't invest that much in offshore wind. When we allow these interconnectors, the optimal configuration brings this offshore wind to the system. And probably the most benefited systems here are Netherlands and Germany, because of their lower availability of onshore energy. They import large amounts of energy. And now we bring the hydrogen part to the table, because in this previous case study, we only included the offshore power in the grid. But in the case studies that we were evaluating, there's a large demand of hydrogen onshore. Of course, these scenarios are very stringent. They aim to decarbonize also international transport and industry feedstock. But we are talking about 6 exajoules of hydrogen demand in the North Sea region, which is a quite considerable amount. So our question was, okay, what will happen if we allow the model to invest also in hydrogen interconnectors from these hubs to the nearest point in the shore? So with this setup, the model can decide if it's more cost effective to invest only on power interconnectors or hydrogen. For the reference case, we found out that the Netherlands found this transport method more interesting than power. And actually over 1 exajoule of hydrogen was produced offshore. So we assume that the electrolyzers are placed in the energy hubs and are transported via hydrogen pipelines to shore. But in this reference case, rest of the countries decided to import electricity only and produce the hydrogen onshore for different end uses. And we extended this case to another scenario in which offshore potentials are higher. Those offshore potentials are extremely high, are based on espresso projections. But the moment the offshore wind potentials grow, the transport of hydrogen starts being more interesting. And the reason might be that with these rates of power interconnector, the system doesn't need more power interconnector, and therefore hydrogen pipelines, which are in general a bit cheaper, are more cost effective. And in this setup, a very large amount of hydrogen, 2.1 exajoules, is produced offshore and is brought to shore for end uses, which are mainly synthetic fuels and electro feedstocks. And yeah, I think with this one we can finish. We have some time for discussion. So yeah, I will stop here. So thank you very much. I will. Oops.
Okay, thanks, Raphael.
Yeah, I can stop sharing. Yeah, sure.
That's great. So who's the start of some questions? Now is the time where the audience can get involved. Don't raise your hands or type in the chat if you have a question. Maybe I could try to start us off. So Raphael, about your presentation. I mean, I like the formulation of this new model, the way it's whole North Sea region. I just wonder about the system boundary and what impact it has, because as far as I understand the way it's formulated, it sort of cuts off the, put it another way, the neighboring countries of the countries on the North Sea are the sort of like the countries themselves, the model does know. So I just wondered if what do you think the implications are of doing that?
I don't know if it's my headphones, but I think I cannot listen to you properly. So can you?
Yeah, I think I got an issue with the microphone. Is that better?
Yeah, that's a lot better, Russell. He's right. It's when you lean forward, like this much forward, that it works. It may be a bit uncomfortable, but it helps.
Okay, I'll try that. Yeah, sorry.
Much better.
Just asking about the system boundary for your model, right? So saying you've got the countries around the North Sea, but then you cut off, and obviously all models have to have a boundary somewhere. So, but I was just wondering, in this particular instance, what do you think the implications are of this system boundary? So the fact that the neighboring countries, through the countries that border on the North Sea, are not really included, and what impact that has for, you know, energy flows, power, but also other gas, hydrogen, or whatever.
Yeah, that's a good question, and that's actually how we started. We started only with 7 North Sea countries, and the neighboring countries or the rest of Europe, we modeled them in a very dummy way, and we found out that when we included the rest of Europe, there was a large difference in the results, because yeah, I think it's also proved in many other studies that when you go for a larger amount of renewables, interconnectors are extremely important, and the flexibility that they provide is extremely big. So that's why we decided for the North Sea, we include all the energy sectors. For the rest of Europe, of course, that's not computationally feasible, but we included only power. So the model itself can decide to invest in additional capacity in the rest of the countries to capture these import-export flows. And this made a really big difference, especially, for example, the import and export dynamics from France to UK, France to Belgium, also from Germany to Southeastern Europe. There are big differences there if we don't consider them. So that was really a decision that we had to do.
Okay, good, thank you. Maybe a question to, just before, let's take that question after. I just wanted to ask Luca a quick question about, well, also to you, Raphael, if you have a comment, but it's mainly to Luca, about the temporal resolution of your demand profiles, right? So I think you said you took average, something like average profiles, and I just wonder, how well does that reflect the industry, where they more or less have a steady state operation on these platforms, or are there occasions when you have peaks, and if so, you know, are you missing those peaks by taking the average?
Yes, so indeed, in the process type of analysis, we have what we actually did was discretize the lifetime of these offshore areas in normally in 3 phases, which is a peak demand and midlife demand and tail years demand. And then we have different instances. Then we also have a discretization throughout the year with a resolution of 1 hour, because we were checking the wind contribution. So if we need to provide, say, 30 megawatt and the wind, we have a wind farm of 30 megawatt, but maybe sometimes it does provide all the 30, sometimes provide 15, sometimes does not provide. So for every hour, we were calculating what we need to do to meet this power demand. So what we haven't been taking into account is like the yearly variation, the variation throughout the year of the power and the demand of a platform, which indeed is not constant, of course, but will be changing and having peaks and decreasing in that. So we didn't do that not to make everything more computationally intensive, of course, but it's something that we are thinking to include and looking at to going towards uncertainty, optimization under uncertainty type of analysis, but we haven't been doing that yet.
Okay, sounds good. Thanks. So we have this question. Someone has asked, what are your views about the asset life of offshore wind farms and oil and gas installations? Did either of you want to comment on that?
Well, I must say not too much from my side, but what I can say is that what we were assessing was the entire life of the oil and gas installation, which is the life until there is some oil in the reservoir, and then that's what we consider also what would be the asset life of it. And then we were also making the assumption that the wind farm would last at least as long as that, but with potential of a longer lifetime. That's also when I was starting to talk about potential for reutilization of hybrid energy system concepts. And then maybe just to conclude is like the lifetime of oil and gas installation. It depends, of course, on the size of the reservoir, but it could be around 15 to 25 years, maybe.
Yeah. Okay. Yes, I would pretty much agree with that. Some of the assumptions that we made, possibly in some cases, the oil and gas infrastructure could be longer than 25 years. It depends. Depends partly on the reservoir, but also on the lifetime of operation. The wind farms, I would have thought of the order of 20 to 30 years. So ballpark figure, but it does depend on quite a lot of factors, obviously. Yeah. Rafael, do you have anything to add there?
Not really regarding to oil and gas. And regarding wind, that's a good point actually, because in these models we usually don't consider the end of the lifetime. Usually it's like 30 years of life cycle, but we don't consider what will happen after that, and that's what that might be a big problem in the future. Yeah, so far in the analysis we are doing, we are not considering that that end of the life cycle, but yeah, that's a big topic.
So okay. I wonder about future research avenues. If maybe we could highlight some pathways or urgent further research that we want to do. And certainly from my perspective, there's to improve the quality, let's say, of modeling of both types of infrastructure, oil and gas and renewable, and to improve some of the assumptions that we made in this quite simplified study for Denmark. It wouldn't have to be within a Balmoral framework. We did use that, but now we have this open source model that we showed us up there. That would be an option. Yeah, or maybe to connect some of these different models. So, Luca's approach at a platform level with a higher level. Yeah, I mean, what are your thoughts, either of you, about direction, further improvements in the near future?
At least from my side, what I'm working now, and I expect to to have some results by the end of the year probably, because now the clustering that we are doing and the data that we use to define regions is mostly offshore wind, but we have a lot of data and we have some colleagues working with oil and gas data and GIS and spatial analysis. So we want to try to overlap wind data with oil and gas platform data with probably salt caverns or other type of reservoirs where we can store hydrogen, for example. And with these different layers to create regions that can be totally interconnected in terms of sectors. And therefore, we could really also include existing oil and gas infrastructure, because in the results that we got a relatively optimistic potential of, or like a decent transport of hydrogen to shore, around 1 exajoule, I think, in this case. And this is considering new infrastructure. If we start assuming that reusing assets from oil and gas industry can bring this cost down, maybe these numbers go even up. So that's the next step of this for my case.
Okay. Are you also, because you said you've got these different layers, you're also looking at, you said salt caverns, but also the reservoirs as potential storage options as well. So like abandoned or depleted reservoir could be a storage for CO2 or hydrogen.
Yeah, and that's also a point for CO2. We're also thinking of including a potential there. So the idea is to have a complete offshore grid of hydrogen, power, CO2. And yeah, the model has the capabilities to include all these activities in offshore regions. And so far, we are not finding computational problems when adding more nodes. So I think we can eventually reach a very decent level of spatial resolution. So, yeah.
Yes, Luca, anything to add?
Yes, well, there are many things ongoing or planned. So first, I should mention that my colleagues from the electrical engineering department are running experimental campaigns in which they will test the grid stability, electrical grid stability in hardware in the loop type of setting, where then the fuel cell and electrolyzer stacks will be simulated, and then while we have the physical hardware for the grid components. And they will also developing a new hybrid solution for storage. So far, the main responsible for dealing with the irregular contribution of wind would have been the fuel cell and electrolyzer stacks, and to some extent the gas turbine. But then problems of degradation might arise. So we are thinking to develop an hybrid structure in which we have batteries to take care of the very short-term type of oscillation, while the fuel cell and the electrolyzer stacks take care of the more to smooth out than the entire behavior. And then, of course, something that I mentioned is that we would like to look at techno-economic analysis of this, and eventually also looking at how to improve the concept. For example, having a more in-depth look in concept of using hydrogen into the gas turbines, because that there could be some limitation in terms of what kind of combustion technology is used or not. And so we will try to improve the performance also in that direction.
Right, sounds good. Like a long list of things to do to keep us busy. Yeah, sounds good. One idea that's been discussed a lot in this context is the idea of, because I mentioned the pipeline issue with hydrogen and embrittlement, and one idea is to have this hub offshore where it could be like a refueling station for ships, or so that your transport option is more by ship than by pipeline. Is that something you're also looking at?
Well, in my case, no, because what we realize is, well, we are using hydrogen locally, at least for the time being, and the energy consumption for liquefaction would be too high to make the whole concept energy efficient. But I believe that maybe for if we're going to look in the long term to make this as an energy hub, and with exporting hydrogen to shore, the liquefied hydrogen could become a very interesting possibility indeed.
What about you, Raphael?
Yeah, I totally agree. Like so far in the analysis we've done, we only consider pipeline infrastructure,
Yeah.
but yeah, for sure in the future we'll consider also ship transport because it can be cost efficient. Yeah, we can let the model decide which option is more attractive. So yeah, for sure that's something that's on the table.
Yeah. Sounds good. We're just running out of time. There is another question here. I think it's kind of difficult to answer because it's quite general, right? I don't know, Luca, do you have a comment there about the average size of investment or capacity for one of your hybrid system projects?
Yes, it is indeed very difficult, and I would love to have more elements. But as I mentioned, the costing, we haven't arrived yet to costing. So, and then I guess that also to answer properly, we would probably discuss the boundary of this maritime sector solution.
Yeah.
So sorry, I cannot really answer at this point. I would say.
Yeah, I agree. I think it's interesting. Let's maybe take this conversation offline and continue. And by all means, if you're in the audience, and we can follow up with some of these questions. But I think we're out of time for the discussion. So I'd just like to thank the panelists, Raphael and Luca, for participating in the nice presentations and discussion. Thanks to the participants in the room. Just like to remind you that it's in the chat as well. There is a meetup in half an hour for drinks apparently. So if you go to the bar and get some drink and in a special room, you can see all the posters session there. So yeah, thanks to everybody and enjoy the rest of the afternoon.
Thank you. Goodbye.
Thank you, Russell. Have a good evening, everyone.